All right, so here we go. So now we finally get to use that different kind of multiplication. So remember when I talked about AB equaling the matrix A times B1, the matrix A times B2, dot, 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 right? Up to the matrix A times BP, wherever that could be, needed to be. All right, here we are being told what the matrix AB is. And here we have the matrix A. So what we know is that this right here is A, B1. And what we're being asked to find is what B1 is equal to. So here I have A. So I have A, B1 is equal to this. So let me just write down what I have. A, B1 is equal to negative 1, 6. And what I'm being asked to find is what the vector B1 is. So let's look at this. If I put the matrix A in, trying to find the vector B, the column vector B1, because it's equal to negative 1, 6. Well, this is an augmented matrix. So if I can solve for B1 by putting together the augmented matrix and solving, so reduced row echelon in my calculator gives me this. So this means that my B1 vector is 7, 4. All right. So moving on to some more thoughtful questions. Okay, so what if I want to show if the columns of B are linearly dependent, so are the columns of AB. Okay, so let's think about what linear independence and dependence, what's the contrast? So we know by definition, so there's not a pivot in every column, that's true, but also don't we know that there has to be a non-trivial solution? So Bx equals 0 must have, but has a non-trivial solution. Because if it was independent, Bx equals 0 would have just a trivial solution. Okay, so I'm going to start with that. And then I'm going to take and multiply A on both sides. Now it is important that you make sure that you multiply both sides on the left-hand side, right? Order matters of how you multiply. So this is the matrix AB times X. And here I have a matrix A times the 0 vector. Well, that's going to give us the 0. Okay, so what do I know now? Here I had X being not 0, right? There is a non-trivial solution. I still have AB X equals 0. So this shows that ABX has a non-trivial solution. And so what that means is that AB matrix has linearly dependent columns. All right. So let's look at what we've got next here. All right, so here we have a matrix B. And this matrix B is such that the third column is the sum of the first two columns. All right, so let's put together our matrix B. So here would be column 1, here would be column 2, and then the third column would be B1 plus B2. Okay. So now what, so this is column 1, 2, and 3, right? Okay, so what can we say about the third column of the matrix AB? All right, so if I'm going to find the matrix AB, that means I'm taking A times the matrix B. So by doing my matrix multiplication, I'm going to take the matrix A times column B1, matrix A times column B2, and matrix A times the third column, which is this. So the third, what can we say about the third column of the matrix AB? So the third column the column of AB is A times B1 plus B2, which is the same as saying AB1 plus AB2. And so it is the sum of the first two columns as well. So just using this multiplied by A. All right. So what can we have here? We have the last column of AB is entirely 0, but B has no zeros. Okay. So we're looking AB, which is A times B1, A times B2, dot, 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 dot. And then just because it's saying the last column, right? So let me just write down ABP, right? So what they're saying is that this last column is all zeros, which means it's a column vector of zeros, right? Dot, 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 dot. Okay, not commas, but dots. Okay. So what can you conclude about the columns of A? All right. So from this, I know this is equal to this, correct? All right. So let's write that off to the side. ABP is equal to the 0 vector. Okay, so what did we know about the matrix B? So the matrix B is just made up of B1, dot, 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 all the way to BP, all separate vectors, and none of the columns, none of the columns are 0, right? So that means that BP is not equal to the 0 vector. BP is not equal to the 0 vector. Well, what that means, since this is not equal to the 0 vector, that the columns of A, right, I have a non-trivial solution. I have a non-trivial solution to ABP equaling 0. So that must mean the columns of A are linearly dependent. All right. So here I'm talking about a transformation from Rn to Rm, and you know that matrix A has to be an M by N matrix, right? Okay. So let's just get a picture going here. So I know it's N this way, right? And M this way. All right. So if I know it is onto, what do I know about the relationship about M and N? So onto means you have to have a pivot every row. So if I have to have a pivot every row, that means that the number N has to be bigger than or equal to M. I'm going to have a pivot every row, right? This number here has to be larger than this. Otherwise, I run into the problem of like a short, long equal, anyway, so N, yeah, it has to be, sorry, I was doing that wrong. If I have it this way, right, lots this way, I can't possibly, if I have a 4 by 2, I can't possibly have a pivot every row. So N, the distance this way, has to be bigger than or equal to the distance this way. Okay, so what do I know about 1 to 1? In order to be 1 to 1, I have to have a pivot every column. So that must mean that M has to be bigger than or equal to N. In order to have a pivot every column, M has to be bigger than N.